Here we're going to look at an optimization problem, and because this is such a difficult topic for at least my students, I'm probably going to do a bunch of videos on optimization, and it follows naturally from what we've been talking about in the previous videos where we were trying to find maxes and mins of functions using calculus. So we're doing the same thing here with optimization problems. The difference is that we're going to be doing it within the context of a given situation. So we're going to need to interpret our answers correctly. So we'll start with a simple example. It says, find two numbers whose sum is 50 and whose product is a maximum. So the first thing you'll want to do is to model this situation. So I'm going to write this down. To model the situation, I interpret that to mean either draw a picture if necessary, or at the very least, come up with a function that relates to what you're trying to optimize. So we're trying to find two numbers whose product is a maximum. So we're going to want our function to be a product function, and we also want it to be in terms of one variable. So to start with, let's just use the information given. It says find two numbers whose sum is 50. So let's just let x be one of the numbers and y be the other number. So that equation represents two numbers whose sum is 50. Now we're trying to maximize the product. So for now I'm just going to write, okay, well p, that's going to be the product, equals, well if x and y are my two numbers, it's just xy. Now the problem with leaving it like this is a function of two variables and we want it to be a function of one variable. Just imagine trying to put this into your calculator. You can't until you've actually until you've represented it in terms of one variable. So we can do that with a simple substitution. This equation lets me claim that y is 50 minus x. So I can take that and put it in here, and so now I know that the product is x times 50 minus x. And now I can even say p of x, because now it's just in terms of one variable. Alright, so there's my function, and I want to optimize. I want to find a max for that function. So one thing that you can probably do, and I'm sure that it's this day and age it's not so much of a big deal, is you can use your calculator to get a graph of this function just so you know what you're looking at. You would just need, in a calculus course, you would just need to back your answer up or support your answer with calculus. So that's just something I want to throw out there. I'm gonna imagine that we graph this. If we were to graph this function, well, we can tell that its zeros are at 0 and at 50. And we know that the x-axis is just one of my numbers, and the y-axis is my product. So I've got two zeros, and it's a parabola. So if you graph it, it's a parabola whose vertex is a maximum. And if you put this in your calculator, you get a graph like this. And based on our knowledge, even if you didn't graph it, just your knowledge of symmetry of parabolas tells us that that's going to be 25 there. Okay, so already we're making sense of this problem without even using calculus. One thing we could mention too is that, what about the domain of this function? Well, I guess technically numbers go on from, we could consider all numbers positive and negative, but as soon as if I were to go over to 51 here on this graph, well then 51 plus y equals 50 would mean that y would be negative 1, and 50 times negative 1 is going to be a negative number. So if we're looking for the maximum of a product, it doesn't really seem to make sense that we would want to consider negative numbers. So I just sketched my graph on the interval 0 to 50. So the domain of this function, reasonably in this case, would be from 0 to 50. Okay, so to support that our answer here is 25, so one of the numbers would be 25, but to support that using calculus, we're going to solve. And we're going to do that by taking the derivative. So I'm going to represent p of x as 50x minus x squared, so I don't have to use the product rule. P prime of x would therefore be 50 minus 2x. And now what I want to do is to find critical points. I'll set the derivative equal to 0. And solving this tells me that x is 25, just as we suspected. Now it says find two numbers whose sum is 50 and whose product is maximum. So one of the numbers is 25, and the other number would have to be 25, since 25 plus x, or x plus y, is supposed to be 50. So 25 plus y equals 50 implies that y equals 25. Now I kind of glossed over something that's important, which is, are we sure that we found a max at 25? I know that we have the graph in front of us, but we're not always going to have the graph in front of us, and we would want we'd want to ensure that the critical point actually represented a max or a min, because we know that some critical points don't, right? It can just be a stationary point for which there's no max or min. So one thing that's usually good to do is to make yourself, now I know it seems silly in this case since we sort of already know the answer, but it's usually really helpful to make yourself an f prime or a p prime number line in this case, and just evaluate the derivative on these intervals, just so you can convince whoever you're writing this problem for, you know you found a max and it's supported by calculus. So for instance, if you plugged in 10 into your derivative, you would get a positive number. And if you plugged in 30 into your derivative, you would get a negative number, which means we've definitely found a max. The other thing you'd want to do is check endpoints, because remember there could be a max or a min at an endpoint, but we don't need to do that here since there's a min at 0 and there's a min at 50. So those wouldn't need to be considered in this case. But endpoints could be answers to optimization problems, so just be aware of that. And so the last thing we'll do is just interpret our answer. And this is nothing more usually than a sentence that is answering the question asked, and if the units are required, make sure you use the correct units. So no units are required for this problem, so I'll just say the two numbers are 25 and 25. Alright, so there's a simple optimization problem. Mainly there's a nice kind of balance between using your calculator and using calculus. For my students, there's nothing wrong with using your calculator. The point is to make the connection between what calculus can tell us and what the calculator itself is telling us. So you need to make sure you support your answer with calculus like we did here regarding the derivative. So on the next page, I'm going to give you a series of steps that I think will help in any optimization problem. And I'm not usually one to give steps to my students, but I think in this case it might be helpful, at least at the beginning, to have something to kind of work through, and almost like a checklist, and make sure you're doing all those things before you actually finish the problem. So here are just some general steps in any optimization problem. They're worth jotting down, at least at the beginning, until you get the hang of it.